Welcome to ECE 203. This is the second lecture on basic CMOS building blocks. At the end of the previous lecture, we were just discussing the common source amplifier and what some of its metrics were in subthreshold and in above threshold. And we found that for an interesting case in subthreshold, we actually didn't have, as a designer, good control over the gain, which is an interesting, proposition. This is not what we're used to if you are, a typical analog designer operating in above threshold. So what we're going to do today is we're going to look at a few other types of circuits. Specifically, we're going to start by looking at the source follower. Okay, so a source follower looks something like this. We have, in this case, I'll draw it as an NMOS source follower. And it is biased with some current source, I bias. The input voltage is coming in over here, V in, and the output voltage is taken out over here. There are some other elements, RS and CS, in parallel with the output. And we'll call this V out. Now we should note here that the source is not connected to ground, and as a result we probably should specifically indicate what the body voltage is connected to. Typically in these scenarios we will just connect it to ground if this is a bulk CMOS process. So what we'd like to do is derive what the transfer function is from V in to V out. And to do this, we need to, once you have more experience, you could probably just immediately kind of write down the answer. But if you're not sure, the best way to do this is to draw a small signal model. So that's precisely what we will do here. So I'll put my V in as a small signal AC source. This is V in. And then it's going to go into the gate of the transistor. In this particular case, I'm going to include CGS. I'm going to include CGB, and I'm going to include CGD. Okay, so this goes to the drain of the transistor. In this particular case, we have our transconductance, GM times VGS. And we also, in this particular case, because the source voltage is not grounded, it could change. We also have the GMB term in here, GMB times VBS. And then we have our O resistor here. And in this case, the drain of the transistor is VDD, which is an AC ground. So we can indicate that on our small signal diagram here. And then we have our resistor here, RS, and output capacitor CS. And this is the output voltage here. Then I'll just very specifically indicate that this here is the voltage VBS, and this voltage across here is VGS. Okay, so this is our small signal model. What we could do is just kind of dive in and do some Kcl analysis, but maybe it's useful to try and simplify the circuit a little bit. So the first thing we're going to do here is recognize something. Let's take a look at this GMB generator. Okay, this is ground, and this node here is actually V out, and this is GMB times VBS. We know VB, that's the bulk, is 0, so it's basically just V minus VS. VS is just V out, so this is equal to minus GMB times V out. So if we take a look at this circuit, we have V out on one terminal, and then we have a current that depends on V out. So it might be obvious what the next step is, but if it's not, let me just write it out to be very clear. The effective resistance of this current source is V out over the current of the current source, just through Ohm's law. V out we can leave there. The current, as we said, is equal to, we have to get the signs right, it's actually negative GMB times V out, but then there's another negative sign for the direction of the current here. So this is equal to 1 over GMB. So what this means is that this dependent generator, specifically because it only has one variable that's controlling its current, and that variable happens to also be the terminal voltage of the current source, it basically just looks like a resistor. So what we can do is replace it with a resistor of 1 over GMB. Okay, and that's going to simplify our circuit just a little bit here. All right, so I'm actually going to draw the circuit, the simplified circuit, on the next slide, so we can derive some of the, yeah, let's do that on the next slide. Okay, so here is the simplified circuit. So we have Vn, and it goes through, I'm going to call this capacitor here CGD plus CGB. Both are to ground. And then we have a capacitance here, another capacitor over here. This is CGS. We have our main dependent current source generator that we can't simplify because it has two variables in it that aren't directly related to its terminal voltages. Vout. I'm going to just call this one big resistor. R tot is equal to Rs in parallel with Ro in parallel with 1 over GMB. And this here is CS, and this voltage across here is VGS. Okay, so this is a much nicer small signal model. We can go ahead and do some Kcl analysis on this. In particular, I'm going to look at the current going through the dependent current source generator out from the dependent generator and equate that to the currents flowing in all of the other branches. So let's go ahead and do that. Maybe I'll choose a different color here. So GM, the current through the dependent generator is GM times VGS, which is V in minus Vout. This is equal to Vout over R tot, that's the current flowing through that resistor, plus Vout times SCS, that's the current flowing through the CS resistor, plus the current flowing through CGS, which is Vout minus Vin times SCGS. Okay, so that's the KCL. So we can now go ahead and collect terms. Vin on one side, that would be GM plus SCGS. On the left side is equal to Vout times 1 over R tot plus SCS plus SCGS plus GM. Okay, so now we just take the ratio of both sides. We get Vout over Vin is equal to GM plus SCGS divided by GM plus SCGS plus CS plus 1 over R tot. Oops. Let me write that a little better here. 1 over R tot. Okay, so this is the correct expression. It's always kind of messy to have your not obvious where your poles and zeros are. So I'm going to simplify this a little bit in the following way. I'm going to pull out the DC, or the midband gain, I suppose. GM over GM plus 1 over R tot times 1 plus S CGS over R tot, all divided by 1 plus S times CGS plus CS divided by GM plus 1 over R tot. Okay, so that is, I would say, a slightly more useful expression for the gain of this source follower circuit. So what I'd like to do now is, you don't get a whole lot of intuition from this formula, so let's make a few simplifying assumptions and see what happens. Okay, so let's just first of all do this analysis at DC. Okay, if GMB is equal to 0, let's say we're able to connect the source to the bulk somehow, perhaps in an SOI process or perhaps in a triple well bulk CMOS process. Let's say that we're attaching a perfect current source to this circuit, so RL is infinite, or I suppose I should say RS is infinite. And let's say our transistor is perfect as well. It has infinite output impedance. There's no channel length modulation. Then we can say that the DC gain of the circuit is just equal to GM over GM plus 1 over R tot. R tot in this case is infinity. So the gain of this circuit is just 1. All right, this is why we call it a source follower, because whatever comes in at the gate just follows down to the source. Now, naturally, these are assumptions that aren't true in practice. So let's make slightly less assumptions. What happens if only RL, sorry, I should say RS, is infinite, and GMB is not 0 and R naught is not 0? Then we can say that the DC gain is equal to 1 over 1 plus GMB over GM plus 1 over GM RO. And if you put in values for normal processes today, you're going to get something on the order of 0.7 to 0.8. Okay, so technically this is an attenuator, but it's pretty close to a gain of 1, so you can reasonably consider this as a buffer. Okay. Now let's assume that we tie, if the P well is tied to the source. So in other words, if we don't have the GMB term there, then we say that the DC gain is equal to 1 over 1 plus 1 over the intrinsic gain of the transistor, which is GMRO. And in many CMOS processes, this will be on the order of 0.9 to 0.95, something like this. Okay, so the short story here is that the source follower, otherwise known as the common drain amplifier, source follower amplifiers are often used as buffers. So if you want to buffer a signal and it has, you just want to buffer it off chip or something like this so you can observe it, or you just don't need any gain but you need to isolate stages or something like this, a source follower is sometimes a good idea. There are issues with source followers that we'll explore, but they can be effective operating as a buffer. Okay, so we've looked at the common source amplifier and the common drain amplifier. The last one remaining is the common gate amplifier. So why don't we take a look at this one now? Okay, so the common gate amplifier, we typically model this, although it's not strictly necessary, but we typically model this as having a current source at the input. So let me just go ahead and draw the load of this amplifier first, just so my vertical dimension works out well. So we have our amplifier, we bias it with some bias current, I bias. That biasing source has typically some resistance, Rs, associated with it. And then we have our input signal coming in as a current. So we'll call this I in. Now the gate can't just be floating, it has to be biased at some bias voltage, V bias. This is resistance RL, and we pull our output over here. Okay, so this is a classic common gate amplifier. Again, we should probably specify what the bulk voltage is, because it will come into play here when we draw our small signal model. So what is the gain of this circuit? Again, the best way to get started here is draw the small signal model. So let's go ahead and do that. Again, I'll start at the top here. I have CGD plus CDB, and that is in parallel with the load resistance, RL. I'm drawing the other terminal of CGD and CDB as a VDD, although we recognize that this is just a small signal ground, so I suppose I could just make these ground symbols here. In this case, we have our dependent current source generator, and in this particular case, the gate voltage is DC. Okay, so GM VGS is really just minus GM times VS. Likewise, GMB VBS is similar because VB is also grounded. So this ends up being minus GM plus GMB times VS. Okay, and that's specifically because the gate voltage and the bulk voltage are both grounded in this particular example. Okay, we have our resistor RO there. And then we have a bunch of stuff at the bottom of this amplifier. We have CGS here. We have CSB over here. And again, it's CGS because the gate is grounded. So the capacitor is, I suppose, flipped from what you would normally consider, although capacitors are symmetric, so it doesn't really matter. And then we have our input current, I in. Now, this node here is called VS, and this node here is V out. Okay, so what we'd like to do is find what is the gain of this circuit. Now remember, our input is now a current in the circuit, so we want to figure out what the output voltage is. But in this particular case, we're going to actually recognize that we're mostly interested in actually finding out what this output current here is, I.O. I.O. we know is going to pass over RL and CGD and CDB. And if we ignore RO, all of it will go across RL and CGD and CDB. Okay, so let's do the analysis ignoring RO. That's going to make our life a lot easier. Okay, so if we ignore RO, then IO is just equal to GM plus GMB times VS. Simple. All we need to do now is figure out what VS is. All right, so VS is equal to I in minus IO times the impedance at the node there, which is RS, plus 1 over S CGS plus CSB. Okay, so then we can solve and figure out what the transfer function between I in to I out is, or IO, and that's equal to GM plus GMB divided by GM plus GMB plus S times CGS plus CSB plus 1 over RS. Okay, normally when we design an amplifier, we tend to design the amplifier to have relatively large GM so that we can, we typically get better gain by doing so. And usually RS, it's a current source that's causing this parasitic resistance, and it's usually designed to be very large. So the 1 over RS term is usually pretty small. And if our device is small or our frequency is low, our capacitive term will basically be pretty small as well. So this is going to be roughly equal to 1. Okay, so again, this is, I should say, for low frequency and large RS. Okay, so what this means then is if you put in a current into the source of a transistor operating as a common gate amplifier, then ignoring RO and low frequency, large RS, etc., when we make these proper assumptions, or these assumptions rather, we'll find that the input current will just basically make its way to the output. Okay, so if we want to derive what the actual gain of the circuit is, then what we need to do is figure out what the output resistance is, or output impedance is, and then we can go ahead and calculate what that gain would be. So let's go ahead and do that. So I'm going to ask a question. This is certainly an appropriate type of question for an exam or something like this, is calculate the low frequency And when we say low frequency, we really usually mean, ignore the capacitors. Output resistance. Okay, so in this particular case, I want to ignore the capacitors, but I want to include RO this time because it turns out to be important. Okay, so what I'm going to do here is I'm going to actually ignore the stuff on the top. So on the top we had RL and of course those other two capacitors, but we know whatever output impedance we're going to get, it's just going to end up being in parallel with that. Okay, so I'm going to calculate that ignoring RL. That'll make our lives just a little bit easier. So we can go ahead and draw the circuit model. Again, the circuit model has a dependent generator. I'm going to simplify the circuit model a little bit. GM plus GMB times VS. In this case, I'm now going to include RO. And I'm specifically interested in figuring out what the output impedance is. And so the best way to do this is to apply a test voltage and measure the resulting current. I test. Okay, so let's complete the rest of the circuit here, ignoring all those capacitors. This is just RS. The input source is open circuit because we're doing this via a superposition-like analysis. This is VS, and I just want to emphasize here that the gate is grounded, and this is VGS. Okay, so our job here is we want to figure out what I test is, given that we've applied V test to the output. Now there's a small trick, well, not really a trick, but an easy way to do the analysis is we can recognize that the current flowing through this RS resistor must also be equal to I test, right? So all of the current will flow through the current generator and RO, and eventually there's nowhere else for it to go. It has to also flow down over here. So what we can go ahead and say then is that VS is equal to I test times RS. Okay, that just simplifies our analysis quite a bit. Otherwise, we have to do more complicated Kcl. Okay, so we can go ahead and start the derivation. We say that I test is equal to minus GM plus GMB times VS plus V test minus VS over RO. So this is just the Kcl equation at the output node. And we already have an expression for VS. We wrote it down up there. We can just substitute in. And so what we can say then is that R out is just V test over I test is equal to, and I'm going to simplify, or I'm going to skip the algebra rather, just so we can, I don't want to spend all this time on algebra. Just write down the answer. It's RO times 1 plus GM plus GMB times RS plus RS over RO. Okay, so we can make a few simplifications here. We can say that, well, GM plus GMB times RS, that's going to be probably pretty high, much larger than 1, probably larger than RS over RO, so we can get rid of that term. And so basically what we get is something that is RO times GM plus GMB times RS. Okay, and we will note here that this can be very large. Okay, compared to a common source amplifier, which has R out, it's just equal to RO, right? So in this case, a common source amplifier has an output resistance of RO. We have RO times RS times GM. Okay, so again, if GM is large or if RS is large, then this will certainly be bigger than what we had before. Okay, so that's cool. I want to introduce one more, let's call it a tidbit, and say that Rin of this amplifier is approximately equal to 1 over GM plus GMB. I'm not deriving this, I'm just stating the answer. If RL is much lower than RO. Okay, and so this turns out to be useful for low Rin designs, which is cool. I mean, you know, sometimes you need to make a design that has a low input impedance. You know, for example, maybe an RF amplifier that needs to be 50 ohms, or you know, something like this. This is one possible way to do that. Or it's equal to RL over GM plus GMB times RO if RL is much larger than RO. Okay, so that's something you can maybe, you know, kind of keep in your back pocket if you need to, you know, design something with these sort of specs. So the next structure I want to look at is the Cascode Amplifier. Okay, and the Cascode Amplifier is nothing more than stacking two transistors on top of each other as follows. The first transistor has the voltage Vin coming in. We'll call this transistor M1. And what this does is it generates a current. It's a transconductor, right? It generates a current I1 that then goes into a second transistor whose gate is connected to some bias voltage. This transistor is called M2, which generates a current I0 and a voltage at the output VO. Of course, the voltage at the output depends on what's loading it there, but this is the kind of the general case here. So in this case, what we can say is that transistor M1 is a common source amplifier. All right, and therefore what we can say is it's just, you know, a linear transconductor. I1 is equal to GM1 times Vin. All right, so whatever current comes in at the input, this generates a corresponding, or sorry, whatever voltage comes in at the input, this generates a corresponding current running through the amplifier. M2 is effectively a common gate amplifier, right? The current, it has a current coming into its source, and we are looking at the current flowing out of the drain. And so we can say that I0 is, again, approximately equal to I1, which is equal to, again, GM1 times Vin. Now that is an approximation because when we derived the current gain of our common gate amplifier, we ignored RO, but it turns out that this is a semi-reasonable approximation that we can make. So if we want to go ahead now and calculate what the output voltage is, we can say that the output voltage is I0 times the output resistance of the circuit. Boy, you know, wouldn't it be nice if we already had the value of the output resistance of the circuit? Well, if only we had derived this in the previous slide. Oh, we did. Okay, so the current is just, as we said, GM1 times Vin. And the output resistance is nothing more than the output resistance of a common gate amplifier where the RS resistance, or the RL resistance, I should say, RS resistance is just the resistance of M1, which we know is just RO, or in this case, RO1. So we say here that it is equal to the output resistance is RO2 times 1 plus GM2 plus GMB2 times RO1. Okay. Sorry, there's a bracket issue going on here, but I guess maybe we'll just, let's just get rid of this 1 times. This will make it easier to follow here. Okay, so what we can say then is that the gain of this circuit here, AV, is equal to VO over V in, is approximately equal to, well, this output voltage divided by the input voltage, which is, you know, just sitting right there. So we take the input voltage on the other side. It's GM1 times RO2 times GM2 plus GMB2 times RO1. Okay, which is, if we assume that the transistors have same size, same current, obviously, very similar properties, then we can say this is approximately equal to GMRO squared. All right, so this is a major benefit. A normal common source amplifier offers a gain, an intrinsic gain of GMRO, and a Cascode amplifier offers GMRO squared. All right, so Cascodes offer higher intrinsic gain. Now, you know, this was based on a few simplifying assumptions. You know, when you go ahead and actually analyze this more carefully, you'll find that there's, you know, other trade-offs at work here. There's also other benefits. In fact, I'll just write this: other benefits not discussed. You know, very briefly, you can think of something like isolation. Normally we have this CGD capacitor, and that can provide some Miller multiplication of that capacitor, which can, you know, unduly load your circuit. And the Cascode offers a little bit more isolation of that because the voltage gain doesn't happen at the I1 node. You know, there's benefits like this. So what I'd like to do now is move on to a slightly different kind of building block, although it's still related to amplifier certainly, and that is the differential amplifier. Okay, so what is a differential amplifier? Well, by definition, it amplifies the difference between two signals. And I mean, you could argue that, well, even our common source amplifier was doing that. It was amplifying the difference between our one signal and ground. I mean, a voltage is, after all, a potential difference. But in this case, we're going to specifically say that it'll amplify to, you know, a differential signal. Okay, so in this particular course, we're interested in monitoring things like ECG, the electrocardiogram. This is the electrical activity of the heart. Now, we don't know how to build an amplifier that will do this yet, but let's assume that we're going to use our, you know, we could do this, for example, with our common source amplifier. So we don't, you know, at least at this stage, know anything about how the heart works or how electrodes and so on work with the body. But let's assume that we have our nice heart here, and I feel like I drew that pretty well. Very anatomically correct, or rather incorrect, of course. So let's say we have two electrodes that we put, you know, across the heart somehow. Well, we could do the following. We could take one of these electrodes and have it go into a common source amplifier whose other terminal is just, you know, ground here. So we're amplifying the difference basically between these two signals, and this is our output voltage. So this would be what we'd call circuit ground. Okay, so this certainly is one way that you could do this. However, if there's any common mode interference, that comes into play here, which is something that happens when we're dealing with measurements on the human body. We typically exist in industrial environments, in societies that have power, right? And power is typically delivered to our homes, offices, and so on through mains that are running at 60 hertz, at least in North America, 50 hertz in some other places in the world. So we can say that 60 hertz interference, which will likely couple either directly onto the ground node or onto your signal path, or one of the two, probably not both in the same way, can corrupt the signal of interest. In this case, ECG. Okay, so one possible solution to this, I guess I'll call it solution 1, and note that we will discuss ECG in much more detail later, is to do the following. So we'll take our heart again. That's a less good drawing of a heart, but it'll have to do. We'll put our electrodes across it, and we'll put it into what we call a differential amplifier, something that looks like this. Okay, that looks kind of like an op-amp. We'll talk about op-amps and what that means and so on later. So doing something like this can help reject what we would call a common mode interference. Okay, like 60 hertz. All right. Now there are other techniques we can use to cancel some of this common mode interference, but for now, going to a differential architecture is reasonable. Okay, and the idea here is if you do get common mode interference coupling onto your circuit, then as long as the interference is the same on both the positive and the negative terminal of the amplifier, there will be no potential difference between those terminals, and therefore that common mode interference will not be amplified ideally. Of course, in practice, this can and will happen, but ideally it shouldn't. Okay, so what I'd like to do now is show you the kind of very basic way that we could build a differential amplifier. And that would involve taking 2 transistors. Let's see here. Tying their sources together, biasing it through some bias current, I bias, and attaching it to some load. Okay, so we'll say this is V in 1, this is V in 2, and this over here is what we call V out 2, and this is V out 1. And these load resistors are RLs. Okay, so this is a very basic differential mode amplifier. Now I was specific in the choice of notation of these variables here. These are supposed to be AC plus DC signals here. So if that's the case, what we can do is we can go ahead and we can plot the large signal behavior of this circuit. So what I'd like to plot here is on the x-axis, I want to take V in 1 minus V in 2. And I want to plot V out 1 and V out 2. Okay, so let's just think about this for a moment. If V in 1 is very large and V in 2 is very small, then all of the current, the bias current, is going to want to flow through V in 1. None of it's going to flow through V in 2, right? So if we have a lot of current flowing through V in 1, then that means we're going to have a large IR drop across RL in the V out 1 path. As a result, V out is going to be VDD minus this IR drop. Okay, so we can say on the low end over here, this is going to be what we'll call, I'll just put a little label to it here, VDD minus I bias times RL. So we say that Vout1, when Vin1 minus Vin2 are high, is going to be somewhere over here. Now, likewise, in that very same condition, when Vn1 is much larger than Vn2, then Vn2 is very small, and as a result, no or very little of I bias flows through it, and as a result, there's no IR drop or very little IR drop across RL, and as a result, its voltage is basically just VDD. Okay, so we say on the upper end here, the voltage is equal to VDD, and we say that Vout2 is up here, and I apologize, this should have been in capital letters, Vout1 down here. Now, as you can imagine, the opposite scenario happens on the other side of the curve. Vout1 is high when Vn1 minus Vn2 is negative, and likewise over here. Now, obviously, these curves have to meet somewhere. It turns out that they meet in the center of the plot here, assuming the circuit is symmetric, and that is when the current is flowing equally between them, which means that the output voltage will be VDD minus 1/2 times I bias times RL. Okay, so it turns out that the curves look, something kind of like this. Okay, that would be Vout1, and then Vout2 looks something like that. Okay, it should be perfectly symmetric. My drawing's not perfect, but I think you get the point here. All right, so what we often like to do when we talk about a differential amplifier is we like to separate the input signal into a differential mode signal and a common mode signal. We do that with the following kind of circuit representation. We say that we have some common mode signal, VCM, that on top of which we build a differential mode signal. So this would be V differential mode over 2, and this creates our V in 1 terminal. Then we have the exact same voltage source. In this case, even the polarity of the label is the same, but its polarity in the circuit is the opposite, and that is V in 2. So we say here that VCM is the common mode voltage. VDM is the differential mode voltage, or the differential signal. And ideally, the differential amplifier, the differential amplifier should work independent of VCM. We'll find out that that's not totally true. Most differential amplifiers have a finite common mode rejection ratio, but to first order, I think this is a reasonable assumption. So I'd like to spend a little bit of time analyzing the behavior of those transistors in our differential amplifier, which we call differential pairs, or diff pairs. Okay, so let's ignore, the resistors attached to it. Let's just look at the transfer function from the voltages to the currents. So we can go ahead and draw our circuit model. It looks something like this. We have our bias current, I bias, and we have V in 1. And again, I'm going to keep these as large signal parameters here. They're going to be AC plus DC components. This node here we'll call Vx. We'll note that this is transistor M1, this is transistor M2, and I'm specifically interested in looking at the current I1 and the current I2 flowing through the circuit, assuming that we have some loading, some resistors or some transistors or something going on up there. Okay, so what we're going to say here is that if I bias is small, and I guess it depends on the size of transistors M1 and M2, but we can say that M1, at least for the purposes of this analysis, M1 and M2 are in subthreshold. So let's assume that they're in subthreshold and assume they're saturated. We'll assume they're saturated. Let's ignore the body effect, which does come into play here, but we'll ignore it for now. And we'll also ignore Dibble. Then what we can do is we can actually just directly write an expression for the differential output current. Okay, it is ID comma out, and this is again large signal, just I1 minus I2. Now these are both in subthreshold, so it's equal to I off times E to the V in 1 minus Vx over n phi t minus E to the V in 2 minus Vx over n phi t. Right, we have our two exponential functions here. So what we can say is that I1 over I2 is just equal to E to the V in 1 minus V in 2 over n phi t. So if we just take the ratio of those two guys, we get this expression here. So I'm going to do something a little strange, but hopefully it will make sense shortly why I'm doing this. So what I'm going to do is I'm going to take the ratio of I1 over I1 plus I2, which is nothing more than I1 over I bias, right? Because I1 plus I2 must equal to I bias. And I'm going to substitute for I1 and I2 here, okay? Specifically according to the relation that I just put on the line above there. So I'm going to say that I1 is actually just equal to I2 times E to the V in 1 minus V in 2 over n phi t divided by I2 times E to the, well, you get the idea, blah, 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 plus I2 itself. Okay, so naturally these I2s cancel. And what we can do is we can go ahead and say that I1 is equal to I bias divided by 1 plus E to the minus V in 1 minus V in 2 over n phi t. It gets a little annoying writing all these exponentials and denominators and so on, but I think you get the idea. Okay, similarly, let's just get these doodles out here. Similarly, we can say that I2 is also equal to the same thing, I bias divided by 1 plus E to the plus V in 1 minus V in 2 over n phi t. Okay, so maybe some of you may know where I'm going with this, but if you don't, bear with me. So we can now, we have an expression for I1 and I2 in terms of I bias and the differential input voltage. So let's go ahead and figure out what the output differential current should look like, ID out. Again, this is just I1 minus I2. So we can go ahead and do that, and I bias factors out. And we get the following expression. We get 1 over 1 plus e to the minus x, where x in this case is just v in 1 minus v in 2 over n phi t. I'm just replacing that with x to make this easier. Minus 1 over 1 plus e to the plus x. okay, where again x is just equal to Vn1 minus Vn2 over n phi t. So now what I'm going to do is I'm going to multiply, I guess I'm going to do it for this one here. I'm going to multiply by e to the plus x divided by e to the plus x. So I'm going to multiply by 1 to keep the expression constant, but this will simplify something a little bit. And this is now going to be equal to I bias times e to the x minus 1 after adding the terms plus e to the x plus 1. Now, some of you may recognize that. This, as it turns out, is a trigonometric identity, and specifically it is the tanh function. So this is equal to, maybe I'll draw it down here, this is equal to I bias times the tanh of Vn1 minus Vn2 divided by 2n phi t. Okay. Now, what's cool about this is that this is a large signal model. We did not make a small signal approximation here. Okay. So this is a large signal model. So this works for, you know, any magnitude of differential current that you can, or differential input voltage that you can reasonably generate within your circuit. So this is cool. So what we could do now is we could take this expression and try to linearize it if we want to build ourselves a small signal model without having to go through the small signal circuit model. This is the large signal behavior. We could take the derivative and so on. So just to make sure that that last point is well understood, again, we could draw a large signal transfer function. In this case, Vn1 minus Vn2. And we could look at the differential output current. All right. Now again, as we noted earlier, when Vn1 minus Vn2 is very large, then the differential output current will just basically be I bias. And when it is very small, it's going to be minus I bias. Or in other words, the current is just going in the other branch, right? And so we say here that the plot will vary from minus I bias through 0, and then slowly up to plus I bias on this side. Okay, so this point here would actually be 0. Now the idea here is this is the large signal model. So what we could do is we could take this point here and we could linearize across this point. That's supposed to be a straight line. I didn't draw it particularly straight here. But you could linearize here for the small signal model, if that's something that you were interested in doing. The other interesting thing that we could note here is that this sort of differential circuit is capable of both analog functions because it's linear, right? So if we linearize across a 0 current operating point, then or 0 differential current operating point, I should say, then we get a nice linear amplifier. And it also works across digital applications in the nonlinear regime. Because, you know, if Vn1 minus Vn2 is very large, then we're basically getting a, you know, one very specific value of current, and then if it's very negative, then we get the opposite value of current. And so it's kind of a 1, 0, or plus 1, minus 1, if you will, kind of operation. So again, in subthreshold, the differential current of a diff pair is basically just a tangent function. Okay, it's based on the exponential math of subthreshold circuits. Now, just for fun, we can compare this to above threshold. I'm not going to do the derivation. I'm just going to write down the answer. The differential output voltage, if we look at kind of the full-fledged IDS equations, it's equal to I bias times V in 1 minus V in 2 divided by VOV, the overdrive voltage, VGS minus VT, times the square root of 1 minus V in 1 minus V in 2 divided by 2 times VOV squared. So this is a nasty expression. So just to keep in mind, VOV is equal to VGS minus VT when V in 1 is equal to V in 2. Okay, so this is, in above threshold, you get kind of a nasty square root kind of function. It ends up looking somewhat similar. In subthreshold, it's a very nice tangent function. As it turns out, we're going to leverage the fact that it is a tangent function and leverage the fact that we get exponentials as a way to build some kind of neat circuits. All right, the last basic building block I wanted to cover in today's lecture is current mirrors. So we've always shown this kind of ideal bias current that's biasing our differential or our single-ended amplifiers. How do we generate this current source? So we're actually going to talk about how to do current reference generation later on in this course. Let's assume that we have one of these. How would we then, pass it to various of our different amplifiers in our circuit? We do this typically via a circuit called a current mirror. And of course, those of you who've taken the prerequisite courses know very well what a current mirror is. We'll derive the performance in subthreshold, although it won't be too surprising to you. But let's just for a moment go over some of the requirements for a current mirror. It needs to have constant let's fix that. Constant output current, independent of process voltage and temperature variation. We call this PVT. This is an acronym that we tend to use a lot when we write papers and in industry. And it should also ideally have a high output impedance. We want to make sure that it's providing a very large, effective output resistance, so to make sure that we, don't unduly affect the operation of our other corresponding circuits. Now, generally, it's easier to build a known good current source once and then copy it over all across the chip rather than having to build current reference generators for each one of your circuits. So we say generally it's easier to copy what we call a known good current. Usually one that is temperature compensated, something like this. And what I mean by that compensated is that if the temperature of your circuit happens to change, then you'll still get the same current flowing out. And that's not necessarily trivial, right? The thermal voltage of our circuits has a direct, obvious temperature relationship. The threshold voltage of our devices has temperature effects and so on. And so, you have to be very careful about how you do this. And we will ideally talk about this later on in the course. So as I mentioned, the idea here is you have some known good reference current. Let's say it's 10 nanoamps or something like this, but your block doesn't need 10 nanoamps, it needs 100 nanoamps. So what do? Well, you design a network of what you would call current mirrors. And these would basically just create branches that have, current that is mirrored and of a particular value that you're looking for as controlled by the operation of the mirror. Okay, this way you only need to generate your reference generator once, and then you're done. You just have to mirror it all over your chip. So the basic mirror is a fairly simple circuit. What we do is we take our reference current, Iref, and we pass it through a diode-connected transistor. So something like this, where VGS is equal to VDS. Okay. And we take this through to another transistor, which then pulls the current off. So we'll call this here is I out. This node here is Vx, and we'll say that this transistor has a W over L ratio of 2, and this is W over L 1. Okay. Again, if you've studied analog circuit design before, this should be a very familiar structure to you. Let's analyze what happens here in subthreshold and see if we get the same kind of thing happening in subthreshold as we would in above threshold. So in subthreshold, we can say that the reference, Iref, current flowing through transistor M1, is equal to I off 1 times e to the Vx over n phi t. Likewise, I out is equal to I off 2 times e to the Vx over n phi t. They both have the same gate voltage, right? So if I off 1 is equal to I off 2, then I out is simply just a copied version of Iref. Okay? Again, this is ignoring dibble, ignoring channel length modulation, and so on. If, on the other hand, we know that I off is proportional to W over L, so let's say that W over L2 is equal to M times W over L1, then what we can say is that I out is equal to M times I ref. Okay, so this becomes a current multiplier, or divider, if you will, right? So what we typically do is we will generate a single known good current source, Iref, and it'll usually be at fairly low current because it consumes power, and we ideally don't want to consume power in circuits that aren't giving us direct functionality like amplification. And then when we need to bias our amplifiers, we just build a mirror, and we usually mirror the current up. So let's say we need 100 nanoamps. Our reference generator, we'd maybe design it to be 10 nanoamps or 1 nanoamp, and we would multiply it up through this type of current mirror. We can also cascode the current mirrors to improve the output impedance and so on. So all of the kind of good techniques that we know in analog design can be applied here as well.